first of all, the opportunity to speak here. This is joint work with Clemens Rapp, who is also here. And it's one attempt to incorporate and formulate the fundamental theorem of calculus in an abstract differential algebra setting. Of course, we all know the fundamental theorem of calculus, or the two versions of the fundamental theorem. One version says that the integral is the right inverse of the derivation, and the other one tells us also that if we rewrite it a little bit, it tells us that we can formulate the evaluation at a given point in terms of the derivation and the integral. So let's put these things together in an abstract definition. So we start with a differential K algebra over a commutative ring. And we assume, of course, we want to be able to integrate everything, so we assume that the derivation is surjective. And then an integral is just a K-linear operation that is the right inverse of the derivation. So first integrate and then differentiate, I get back the identity. And if we have this second operation on our differential algebra, we can define, we call this triple a generalized integral differential algebra over K, and we can define an evaluation just which we denote by E, by the above formula. It's a very natural definition of what an integral differential algebra could be. And the difference is, until now, there were two approaches, differential text algebras and integral differential algebras. And in both of these approaches, there was an additional requirement, an additional identity on the integral, both motivated from the point that we want to integrate somehow continuous function. So one thing was that the integral should satisfy the Rother-Bext identity. This was worked by Vico, introduced by Vico and here, and studied afterwards with the collaborators. And with Marcus Rosenkrantz, we introduced the notion of integral differential algebras. And there we required that this E is really a point evaluation, that we evaluate the point, and then it's natural to have it that it is multiplicative. So that if you evaluate the product, it's the product of the two evaluations. But we drop these two requirements, we just start with the right inverse. And our goal in the talk is to derive the possible algebra, as many consequences out of these axioms that we can with differential algebra. So the simplest possible example are, of course, the polynomials of an integral differential algebra with the usual derivation and the usual integration. It is in the field of characteristic 0. Of course, then the evaluation that we defined before, here now it's really an evaluation, it just evaluates the polynomial at 0. You might ask yourself, are there other, in analysis, of course, we have many natural examples of differential algebras that are closed under integration, and for which the corresponding evaluation is multiplicative, like the formal power series, smooth analytic functions, or exponential polynomials. All these algebras are closed under integration, and the evaluation corresponds really to a point evaluation. But as soon as, and this was nice for many applications, but of course in many algebraic constructions we would like to start with the rational functions. And then we get into trouble, because then we would have to evaluate at singular points. And the simplest example being is, what if we start with the Laurent polynomials and make, so to say, the integral differential closure, so that it's not closed under integration, but if we add the logarithm, then we have an algebra, a differential algebra with the usual derivation, and we can define an integral recursively, just, okay, on the polynomials we just integrate as usual. And on the rest, we can define integration by the integration by parts formula recursively. This is a definition of an integral. And now you find out the corresponding evaluation. So this is the right inverse of the integral. The corresponding evaluation just gives you the constant term. But in this setting, it's not multiplicative anymore, because if you have x and 1 over x, the evaluation of the product is 1, and the evaluation of the individual terms is equal to 0. And of course, a similar construct, you can think in general, how does the integral if you start from a differential algebra, how does the integral differential closure look like, an algebra which is then also closed under integration. Here in this simple example, you can take the same thing, you can take the integral differential closure of the Laurent series if you want, that's the same definition, but soon if you start with rational functions, and if you want to have an algebra which is then closed under integration, you get into iterated integrals and hyperlogarithms and things like that. These are the two examples. And our goal is now, so we have now three linear operators, the derivation operator, the integral, or the differential operator, the integral, and the evaluation. These are three operations. And we also have the corresponding multiplication operators from our algebra just by multiplying an element with this given element. And our goal is we would like to understand all relations between these operators. So we would like to understand the algebra of integral differential operators. And okay, we will see what understand means, and really also to have a computational handle on this algebra. And what we will use is an algorithmic approach via tensor reduction systems. For tensor algebras, this was introduced already in Bergman's paper on the diamond lemma. In a later subject section, he explains that the diamond lemma for free algebra can also be formulated on tensor algebras, which is a generalization of the free algebra. Then you can also do rewriting and normal forms also on tensor algebras. And what you have to keep in mind is, in this approach, the operator product, the composition is represented by the tensor product. And this is how we formulate and treat the different relations between the operators. And the nice thing is that with this, we don't need to choose a basis for our differential algebra. And so to say, the tensor algebra takes care of all the multilinear structure and the identities. But it forgets all the rest of what our operators, all other identities that our operators satisfy, we have to add by additional relations. Okay, I try to do now in one slide a very informal introduction and description about tensor reduction systems with the simplest operators that we are treating with. So, of course, if you have two multiplication operators, G means multiplying by G and F multiplying by F, and the composition of these two operators, we can, which is then a tensor of length 2, it can be reduced to a tensor of length 1 by just multiplying it by the product of these two multiplication of these two elements. And in general, such a reduction rule is just a homomorphism on the tensor algebra, so where you replace certain tensors by a sum of other tensors, usually of smaller length. So like in Brebner basis computations, you replace the head by the tail of the polynomial that you have here. This is the reduction rule. And as usual, what can happen is you look at the terms, the first occasion when you can apply two different rules. This is then called an ambiguity or an overlap ambiguity in this sense. So if we have a triple product here, then we can apply the rule on the first two tensors, and this is one reduction step, or we can do the reduction on the second step. And the difference between these two things in the reduction system is called an S polynomial. Generalization of an S polynomial. And it's easy to see that since we have an associative algebra, if we look at these S polynomials and then reduce again both sides by applying one more time our reduction rule, we get this, and we denote this reduction by an arrow. So we get the expression below, and this is equal to 0 for all F and G and H just because of associativity. So all, and since here you have to see it for the experts maybe, it's not a single S polynomial, but it's a family of S polynomials. For every F and G and H are just generic, and we have to show that it reduces to 0 for all F and G and H. But here it's very simple because we just use associativity. And the definition is an ambiguity, or such a notation when two such things, when we can apply two different reduction rules on one term or on one tensor is resolvable if all S polynomials can be reduced to 0. And the Theorem lemma in this tensor setting is then, given a tensor reduction system, then you have the following equivalence. Every tensor has a unique normal form, so you have given lots of such reduction rules, and you reply them in any order, and you always end up at the same normal form if and only if all ambiguities are resolved. So all you have to check is you check all possible such ambiguities, check if you can reduce them to 0, and if this is the case, then you have then each tensor has a unique normal form. That's the formula. That's how you can formulate the Theorem lemma in this setting. And in that case, the tensor algebra factored by the reduction ideal, which is just the ideal given by the left-hand side of the homomorphism minus the right-hand side, and the ideal generated in the tensor algebra of these identities, is isomorphic to the algebra of tensors. And what we can do now, we said we wanted to investigate all possible linear relations between the linear operators that we started with: derivation, integral, evaluation, and all the multiplication operators. And from the definition we have, let's first look at a very simple example that we all know, but from this perspective, okay, usually when you introduce differential operators, you start immediately with the normal forms. You say it's a polynomial and you just define the non-commutative multiplication. But in this setting, we could say the differential operators, we have two reduction rules. We have these multiplication rules, we can multiply together, and we have the Leibniz rule, of course, for the multiplication. But then we have an S polynomial. This is the S polynomial that occurs here. If we have a product, derivation, F times F, composed with F, composed with G, then we can apply first on the left, on the first two factors, the Leibniz rule, or we could multiply, use the first rule on the product of F and G and reduce this. And this is now the S polynomial. Now we have to check that this can be reduced to 0 using the two identities that we had before. So what we do is we multiply out in the tensor algebra, and we apply the Leibniz rule on the first term and also on the second tensor. Then we apply again the multiplication rule, and collect all the terms together. And then two tensors cancel. Namely, this one minus this one, this cancels already in the tensor algebra, so it's equal to 0. And what remains here is just the Leibniz rule written in a different way, but only in the ground algebra itself, only in the algebra itself. So we know that this is equal to 0 for all F and G just because of the Leibniz rule in R. This is what we found out, so it's nice. So we have a confluent rewrite system, tensor reduction system for the polynomials, and of course, one thing we forgot, we need one more reduction rule, which looks a bit strange, but if you multiply with the 1 in the ring itself, it's the identity, and we also have an identity in the tensor algebra, which is the empty tensor, so we have to replace the multiplication with the one element by the empty tensor. It's another rule, but to make it simple. And then, of course, if you then apply the theory, we know every differential operator has a unique normal form, and they are just sums of the just the way we write them when if we decide to put the differential operator to the right and the coefficients to the left. And now let's do this procedure Now we have one more operator, so we have the three rules for the differential operators, and now we have two more rules from the fundamental theorem of calculus. If I first integrate and then differentiate, I get the identity. So this product is replaced by the empty tensor. And if I do it in the other way around, I get 1 minus the evaluation, and where 1 is again empty tensor minus the evaluation. So now what we have to do is we have to start to compute such ambiguities and see what happens. And the completion process, or the analog of Buchberger's algorithm in this setting, or Knuth-Bendix's completion, is as you start to compute S polynomials. If one S polynomial does not reduce to 0, this gives you a new rule that you add to your algebra, to your reduction system, and you try to do it. And in a commutative case, it stops and gives you a Brillouin basis, and here generally it does not stop, but in our case, you will see what happens. So a very simple computation. If you have this product, the derivation integral and the get derivation, then we can first, to the first two factors, we could apply that it is a right inverse, or the definition of the evaluation, and then we get the new S polynomials, which tells us the evaluation composed with the derivation, and we know this is 0. So it is not, we cannot reduce it to 0 with the current reduction system because it's not included in our reduction system, but we have to add it to our reduction system. So what we find out, if we evaluate to the constants and then differentiate, it gives 0. Okay, but we didn't know it before. So we just came out of our product, and we can do the analogous thing. So here you have the other ambiguity between the derivation and the integral, and then we find out that if we, so to say, you should imagine it, if you evaluate from 0 to x and then you evaluate at 0, then you get 0. So this is the second rule. So this was not so surprising, but we get two more rules. And now comes a more interesting ambiguity, where we discover a first theorem of calculus just by computing an ambiguity. So this is now we have integral derivation and f, and if you do the computation, you get the new rule. And this rule, I mean, maybe not in this notation, if it looks a bit, maybe not immediately familiar to you, but if we, this is now an operator identity, but if we apply it to a function, we see it just gives integration by parts. So it's, this is now, so now we discovered two things. We discovered a new rule and a new identity that holds in our algebra, which we didn't know at the moment before. So we have integration by parts holds integral differential algebras. The next ambiguity now it becomes more complicated. Now we have a term of length 4. Now we have a new rule, because on this first term here, we can apply now the newly discovered rule that we didn't have before. And on this part, we can apply the rule that this gives the identity. And we do the computation, but the computation is very simple here. And then we get the new one substitution. We get the new rule, which allows you to reduce doubled integrals. Here we integrate twice by a sum of single integrals plus an evaluation term. And this is a variant of the Rother-Baxter identity for the integral operator. In the usual Rother-Baxter integral identity for the integral operator, you would have this term would vanish here, would be 0. And you just say that here you can really see that we use operator notations to avoid parentheses or as many as possible, because and for more details on this modified Rother-Baxter identity, you can also have our poster. Okay. So now, if we put all these completion processes together, now we discovered most of the things, most of the reduction rules we've seen now. There are a few more, like, for example, we discovered this rule, this modified Rother-Baxter identity, which, so to say, reduces this tensor of length 3 to a shorter tensor. And you can also specialize it. If f is replaced to 1, then you get this identity. And in total, we have 14, we discover 14 identities. And all the rest of the identities, they are not so surprised. They are due to the k-linearity of the evaluation. It's kind of simple. But now we want to prove this theorem. And hopefully we have enough time, because now we want to prove that every integral differential operator over an integral differential algebra has a unique normal form with the given reduction system. And what we have to do is now, or what we would have to do is, we would have to check that all S polynomials reduce to 0. So we have seen some of these S polynomials computations, but now we have 14 identities. And in order to reduce such identities to 0, we've seen we had to add, or we had to also use identities in the algebra itself, like the Leibniz rule and so on. And Clemens has implemented a package that allows you to do a lot of this supported by the computer. So what you have to do is, I mean, we have to teach the algebra some basic identities, like how multiplication behaves, how differentiation behaves, the differentiation of the integrals equal to 0. So we have to add a few identities on the differential algebra, and then we have to implement all the reduction rules. So there's just the syntax. We don't have to. It's the table of the rules that we've seen before, just on the computer with the tensor product. So we have these 14 rules. This is then our tensor reduction system. So we have 14 rules. And to prove of the theorem now, we call a command which is called check resolvability, and it tells us that we have 54 ambiguities in total. I mean, S polynomials that we have to 0, and it says all ambiguities are reduced to 0. And to see if we don't believe, or if we want to have more information on this reduction process, we can have a closer trace. So to say, here on this trace, I mean, this is the first thing that we did. This was the overlap between the multiplication operator. We had to apply twice the multiplication rule. This is the second overlap that we computed. It tells us which rule it applied. This was the overlap for the differentiation. And it goes on. So we have to check, we would have to check all these 54 overlap ambiguities and check that they reduce to 0. Here's a particularly long one, so here you have to use 15 rules in order to reduce this to 0. And you could still do this computation for this 54 by hand, but it would be several pages and a lot of patience to do all this reduction by yourself. Okay, and then what we also want to find out is how do the normal forms look like? To which, how much can we reduce it? And what we can do is now we can compute the irreducible words that correspond to irreducible tensors. So here are all irreducible tensors up to length n, 5. And if you put this in the theorem, we can put it together. It's not so complicated. We have the 14 rules, but every integral differential operator in this generalized setting can now be written as a k-linear sum of tensors of diffs length. So we have the differential operators, of course, as a subalgebra. Here we have pure integral operators, but they only need a single integral. But coefficients to the left and to the right, so to say, if you want, the integral is both. And we have two evaluation operators that involve the evaluation, which correspond to evaluations of the derivative at a certain point, or the evaluation of the integral. And we can really now compute constructively in this algebra of integral differential operators, because what do we have to do? If we have two irreducible tensors, we compute the product, and then use the reduction system to find out the normal form. And then you have really, you can effectively compute in this tensor, in this integral differential algebra of operators, computing normal forms, but it's using the 14 rules that we've seen before. So an integral differential operator is, as you can see, the sum of a differential operator, an integral operator, and a boundary operator. And what we said before, we would like to understand all linear relations between these operators. And one way to see it, so to say, is in this reduction system, everything that can be proved in calculus using only equations, it should be possible to derive it using this reduction system, because it includes all possible consequences, only equational consequences of the identities that we had before. And one such example is variations of constants. How to, so to say, interpret and prove variations of constants just using the rules that we learned how to compute this in this generalized setting with differential operators. Okay, so we assume we have the first order differential operator in this algebra, and we have an invertible solution. Then the variations of constants in operator form, this is you take the inverse of the function, you integrate and you multiply by the function, and then the variation, what you have to do is, in variation of constants, or what once formulated would be, you want to check that this V, this is a differential integral operator, is a right inverse of the differential operator. If I first, so to say, compute the solution via integration by constants, but I don't need the arguments, I just do it in the operator algebra and then multiply it with the differential operator, it should reduce to 0. Okay, so the first rule is just computation with differential operator. Since we have a solution, this is equal to, if I apply it to a solution, I just get it in the, I just get the derivation times that's the solution. And then the other identity that I need, so I need to use the Leibniz rule and the fundamental theorem of calculus that it is a right inverse, and then I do the computation, just I apply the successive reduction step, and I find out that this is equal to 1. So this is equal to 1, and so I prove the variation of constants, but then you might wonder, okay, this is a first order differential equation, but the interesting thing is the same computation works for first order systems. There's one, so you just have to replace scalars by matrices and the tensor algebra by the tensor ring. Why is this? Because if we have matrix, so one assumption that we had so far is we always tensored over the rings of constants of our differential algebra. And we assumed this to be a commutative ring. But if we have matrices, then the constants are the constant matrices, and so it's not the commutative ring anymore. So I cannot perform the tensor algebra over the constants, but I have to look at the tensor ring with bimodules. I can just multiply it from both sides. But it's more a technical thing, and it turns out that exactly the same rewrite system works also if you tensor over a non-commutative ring. And so we can prove now the variation of constant for a first order differential system. We now just assume it's just a replacement, but now Z is just represents now a fundamental matrix. Okay, it's exactly the same formula and the same computation, but it gives us the information it works for, and now for an arbitrary size differential system, because here we do not need to speak of a certain size of matrices, but it works for a system of any size, of a generic size, and it's the same computation. So what you can do, this is one conclusion, or one possible application. And the other thing that you could investigate, for example, is Taylor's theorem in this operator setting. So, of course, we know that this is the identity, and then in Taylor's theorem, so to say, to just replace the linear algebra part, you just iterate the identity, you add this identity and compose it, and then this is just linear algebra, this just comes from the right inverse, that you have the identity is equal to the long sum that you have here in terms of operators, and this would be the analytic, so to say, translation, so to say. If you want, this is, here we only use that the integral is the right inverse of the derivation for this formulation of Taylor's theorem. For the second formulation, we now assume that, for the moment, we also assume that the evaluation is multiplicative, because then we have, so what we have here in this rule, what we need to simplify is these iterated integrals. And if we assume that the multiplication is multiplicative, then this last term vanishes, and so I can replace the double integral by the sum of integral of 1 times integral minus integral times integral of 1. And if I use the notation, so if I denote by x the integral of 1 in our algebra, then I get with this identity, the identity that n factorial times the iterated integral is x to the n. And then I have the reduction rule, the double integral reduces this, and multiple integral reduces to a sum like this. And then it becomes more, we see, now the beginning also already then looks, I used this identity and the simplification before, and then this is already familiar version of the Taylor theorem, so I differentiate and evaluate times x to the k, and the, so to say, the remainder term in this general setting cannot really be simplified, but if you write it down in this notation and then you use the binomial theorem, then you just get the usual remainder term. That's the one version. And if you want to give up completely that the evaluation is multiplicative, then you get evaluations at singular points. So to say, evaluations in this generalized sense. And then it becomes more complicated here. You only see the case for n equal 1. So you get the usual, so to say, Taylor polynomial, if you want, but here you have to be careful. Here you evaluate really at the evaluation means not the point evaluation, but just the evaluation in this more general sense at the singular point given by the integral. Then we have the usual remainder term, and then we have, so to say, also a singular remainder term, which we cannot simplify further. And you can also look at the poster for a more general, for a general formula in this setting. For higher order Taylor formula in the generality. And let's do one quick example of the Taylor formula, going back to our example from the introduction. So we have the integral differential closure of the Laurent polynomials, and we take this function, and we want to now develop it in this Taylor series. If you want, that we write down. So we have, okay, the evaluation of f, this was the term, the constant term, so this is 6. The evaluation of the derivative, it gives, is also 1, so we get x. If you compute this term, this gives then, so to say, the usual remainder term of the Taylor formula, and then we have also the singular evaluation term, which is 4, which corrects this term, and then we get an expression. This would be then the development, the Taylor polynomial for this function. This function in this generalized form. Okay, so and here in this case it really corresponds to the regular part and to the singular part. But just final two more remarks. So our big motivation why we studied integrated differential algebras was we wanted to we are working on developing an algebraic approach that allows you to manipulate and solve boundary problems for linear differential equation. And the boundary problem is a differential equation together with some boundary conditions, which make the solutions unique, usually. So you have these two information. So in order just to encode this problem in an algebraic setting, we need to have a differential operator. We need to have boundary conditions or evaluations in our operator algebra. And what we are interested in is in the operator that maps the right-hand side f to the unique solution y, satisfying the differential equation and the boundary condition. And this is called Green's operator, and it's an integral operator. So if we would like to have this Green's operator in our algebra, we also need to have integral operators. And what we've seen is in integral differential algebras, we have, so to say, one evaluation to the constants for free. So we could, in principle, treat initial value problems, but if you want to treat also boundary value problems, we need other linear functionals in our operator algebra. So what you can do, also in this more general setting, you can just add to your algebra arbitrary family of k-linear functional and add the corresponding reduction rules, and then you can compute also this more general algebra. And study by a similar approach that we have, you can then develop quite far a purely algebraic theory of boundary value problems also in this generalized setting that I've presented. Okay, so for the summary and for the outlook, so what we studied, or at least what we tried to study, is the consequences of one formalization of the fundamental theorem of calculus in differential algebra. And we could understand all consequences for the linear operators. Find the influent rewrite system on kernel-based systems. Yeah, we've seen and we've studied the integral differential operators via tensor reduction system, and we've constructed a complete reduction system which allows us to describe normal forms. And using this reduction system, we've seen that you can, for example, prove analogs of variation of constants in the Taylor formula in this generalized setting. And of course, for future work, as I mentioned already, based on our previous work, we can now do an algebraic theory of boundary problems with singularities, also in this generalized setting. And what you've seen is this approach, how to you start with some identities on operators and then try to find a complete reduction system by this completion process. In the tensor algebra, you can add other operators if you want. And one particular that we needed now that came up in application is the shift operator. So if you want to study differential delay equations and you would also like to have the integral in the same algebra, then you get a more complicated operator algebra, you get more identities, 20 for the complete reduction system, but the normal forms look still relatively simple, and we have already one application. For example, there is an integral transform that transforms a differential equation, a differential delay equation, to a differential equation without the delay in some cases. And that's good because then you can apply all that you know for differential equations to differential delay equations. And this transformation can also be discovered and generalized by doing computation in this operator algebra. Yeah, this is one application to algebraic systems here that we're investigating. Another thing, I mean, now we've just seen one example of the completion of the Laurent polynomials, or the integral differential completion of the Laurent polynomials. But of course, we would like to have other computable integral differential algebra. For example, if you start with the rational functions and then have all iterative integrals of rational functions and normal forms in this setting. And from an algebraic point of view, we would also like to, okay, that's okay. Good. You would also like to understand. We would also like to understand free integral differential algebras in this general, the free object in this.
Have you looked at, for example, the ideal structure of the free algebra? I would think of that as an analog of the differential polynomial
Yes.
in the geometry that I might want to create with integral operators.
Yes.
So if you're trying to do geometry, how do you apply this in a geometric setting, adding integrals to the derivatives, the derivations? The way you can add difference operators to differential operators and have differential operators.
Can I ask my question, because I think maybe it's in that. Can
If
I
it
ask
answers my question,
question?
that'd be lovely.
My question would be, how about the algebra of formal pseudo-differential operators, where you can express an integral as a Laurent series in the derivative?
Okay,
Can
these are
you give me an idea of the
but
idea?
these are not completely related questions. So I think what you are asking is, so to say, a generalization of the generalization, or first the generalization of the differential polynomials to integral differential polynomials. How does the free object does the free object look like?
How do you talk about aspect of that? I won't go that far.
Okay, already the ring itself is because I mean, in a special case, not in this general case, we know that so something that we investigated with Lee is if the multiplication is multiplicative, you know how the integral differential polynomials look like. So it's long sums of iterated integrals of differential polynomials. So you can, at least you know how the ring looks like and you can do computations, but to investigate the ideal structure, or of course it would be very nice to understand it more. And
I have another.
Let's thank our speaker and then we'll take the additional questions.
How about this structure is on a integral differential algebra, which I assume is commutative. How about a Lie algebra? Is there such a structure on a Lie algebra so that you can have co-cycles that involve both integrals and derivatives? Sorrow algebra, for example.
I mean, here, one thing is that I remarked with the matrices, so it can be done for non-commutative differential. It's not really, so we don't need commutativity, and also the ring of constants can be non-commutative. So this works. So you can understand the linear operators for other.
Also, Lie algebras would be easier.
No, I wonder if you can couple chain iterated integrals, right? It's a way of computing a fundamental matrix of solution by
iterated integrals.
Yeah. So this is something quite specific, but I think maybe you can tackle the algebra behind chain iterated integrals.
Okay, so
just to Emma's question, one remark is for pseudo differential operators here, we would like to have finite sums in our operators. So our operators should not be infinite sums. So that's why you can, or you.
An integral is an infinite
Yeah, but not from so to say from this operator perspective. No. Here you just look at it as an operator. So and this is just the linear. Yeah, of course, as we said, here we dealt only with the linears.
Yeah. But so the Lie algebras, has anything been done with the Lie algebras in differential? No.
Yeah, I mean, the thing is now that we have a more computer-supported machinery, so to say, to study such completions or rewrites, because if you add a new identity, or one or more identities, it's of course to some extent a heuristic process. In general, it's of course undecidable if you can find normal forms. But you really have to do many experiments to find how to orient your reduction rules so that you get normal forms. And now with the support and this general setting, hopefully we can also study other operators.
So with this Laurent series, right? Or Laurent polynomial, you discuss at end. Is that expansion? Can that expansion give you something about the residue? I'm wondering. So how that is related to the kind of classical theory of expansion?
What would you say?
Yeah, what the concrete evaluation operation amounts to is essentially coefficient extraction. And if you are talking about residues, that's also in some sense coefficient extraction, just not the constant coefficient, but the one below. So if you would apply the evaluation to x times your function, then you will naturally get the coefficient you are looking for when you're taking residues. So that's, so to say, implicitly contained already.
Yeah. Okay. So that's one way to get it. Yeah. So maybe you can ask this group integral. So the other way to. Okay.
One more question.
So in this tensorial notation, you have broken basis. So now, can you divide an operator by another one? Because then you could do the root transformations in your algebra, which is nice.
You want to construct the rings of fraction in this setting. There's some kind of localization. Algebraically. I don't know. Could be possible.
I mean, division should be possible.
Yeah.
Thanks.
All right. The program resumes at 10 a.m. tomorrow on the 6th floor of this building as well. Let's thank our speaker again.